Hi gentlemen, these will be your notes for Unit 0, Day 1 from Calculus. So a reminder that your warm-up, review questions, and some of the example problems will be available in the finished notes. So if I tell you to look back at the finished notes to see whether you guys got them right or wrong, the finished notes are directly above the video notes in your module. So as well as any homework questions you guys had. So homework questions that you guys asked during class will also be available in the finished written notes. So today we're just going to review some ideas about functions, what it is when it's a relation versus what it is when it's a function, the domain, range, intercepts of functions. So we're going to go over all those key ideas today. So a function. Some of you guys might remember different things about a function. Some of the things you guys might remember is that function notation is f of x. You guys might remember something called the vertical line test. All of these are good things to remember about a function. Some of you guys might remember that every x matches to one y. So for instance, if you had a table of values and you had 1, 2, 3, 4, 7, 8, that would be a function because every x is matching to one y. If you had a table of values and x is matched to more than one y, so like 1, 1, 2, 1, and 3, 1, and 1, 2. We have 1 matching with 1, but we also have 1 matching with 2. And I guess I didn't need to repeat that 1. So 1 is pairing with 2 different things. What does that look like on a graph when an x value is pairing with multiple partners? Well, that's where the vertical line test comes into play. So if I plotted the point 1, 1, I'd be right here. And if I plotted the point 1, 2, I'd be here. This function, or this set of points no longer passes the vertical line test, so it's not a function. For something to be a function, every x value needs to be unique, or graphically, it needs to pass the vertical line test. So I'm going to add a page really quick to just draw a couple examples of things that are functions and not functions. So if we had the picture of a circle, which remember the equation of a circle is x squared plus y squared equals the radius squared. A circle is not a function because if you draw a vertical line anywhere on the graph, that vertical line would have more than one point passing through the relation. So if it's not a function, it's called a relation. So anything that relates x and y is called a relation. So this is not a function. Parabolas, the way that we normally think about them as happy or sad, are functions because they pass the vertical line test, or every x value is only paired with one y value. The inverse of a parabola, though, is not a function because it doesn't pass the horizontal line test, which we'll talk about later. So domain and range of a function. Again, these are probably keywords that you guys remember. Domain are the x values that a function can take on, and the range are the y values that a function can take on. So if we had an example of a function, so let's just give ourselves another parabola. So let's say we have y equals x minus 2 squared plus 1. So if you guys might remember some things about transformations, this is a parabola that has moved up 1 and 2 to the right. And it's a happy parabola because it's positive. So I'm just going to sketch a happy parabola that's moved up 1 and to the right. The domain of this function, so all the x values that my parabola could take on, if you imagine those arrows keep expanding up and out, so eventually it'll take on every x value. So the domain of this is all real numbers. And you guys might remember that fancy looking R that could denote all real numbers, or you could say that x can exist between negative infinity and positive infinity, or you can do it with interval notation, if you guys remember with the parentheses. So it exists between negative infinity and positive infinity. The range of this function, so the y values that this function take on, well, the lowest y value that this function will take on is 1, and then it'll keep going higher and higher and higher. So y can be greater than or equal to 1, or in interval notation, it can equal 1, so that would be the hard bracket, and then it can go up to infinity. Infinity is not a real number, so it will always get the parenthesis in interval notation. So the hard bracket is like the greater than or less than sign, and the parentheses is just it's the greater than or equal to sign, or is less than or equal to sign, and then the parentheses is the is less than or is greater than sign. So intercepts. Intercepts are where the graph crosses over the x-axis and where it crosses over the y-axis. So the easiest way you guys probably learned about intercepts are with a line. So if I took the line y equals 1/2 x plus 8, the y-intercept is 8, so 1, 2, 3, 4, 5, 6, 7, 8, and then I'm going up 1 over 2. And so this would be my graph. And so this would be my y-intercept. And then my x-intercept would exist over here. In general, all graphs can have x and y-intercepts, in theory. They don't have to have both, and technically they could have neither. To find an x-intercept, you let y equal 0 and solve for x. So in our example, y equals 1/2 x plus 8, I would have 0 equals 1/2 x plus 8. And then I would just solve. So negative 8 equals 1/2 x, multiply by 2, multiply by 2. And the x-intercept is going to be negative 16. To find a y-intercept, you let x equal 0 and solve for y. So in our example, we would say y equals 1/2 x plus 8. So y is going to equal 1/2 times 0 plus 8. So y equals 8 would be my y-intercept. And you usually list intercepts as ordered pairs. So this would be the point 0, 8, and this would be the point negative 16, 0. And it's the same process for any function, not just lines. So you can use the let x equal 0 and solve for y, and let y equal 0 and solve for x. You can use that process for any type of function to find its intercepts. Now we're going to talk about the parent functions. So if you guys go back to your modules, you can download the parent function file from today's module. Or probably it's called Library Functions and Properties. So we're just going to briefly go through what our parent functions look like and what their domain and range are. So you can always make a table of values to graph. So if I plug in 0, I get 0. If I plug in 1, I get 1. If I plug in -1, I get 1. If I plug in 2, I get 4, so that's going to be off over the graph. So this is going to be the happy parabola. The domain we've already talked about is all real numbers. And then the range of this would be y is greater than or equal to 0, so it's going to go from 0 to infinity. X cubed is the snake-looking graph. And it's going to be a snake whose tail starts down and then goes up. If you guys remember, that's what cubics look like. And the domain of a cubic is going to be all real numbers, and the range of a cubic is going to be all real numbers. The absolute value function, I call it the flying V function. So it almost looks like a parabola, but it's pointed, it's not rounded at the corner. So that's going to be your absolute value function. The domain of an absolute value function is all real numbers. The range of this absolute value function is similar to the parabola. It's going to go from 0 to infinity. So the lowest y value is 0, the highest is infinity. The sine function, maybe you guys remember, you need a couple points to make sine. Sine starts in the middle, and then you would go to pi over 2. The sine at pi over 2 is 1. The sine at pi is 0. The sine at 3 pi over 2 is -1. And then the sine at 2 pi is 0. So the sine function starts at 0 and then goes up. And then on the other side, it forms the same pattern. And so that would be the sine function. And this would be what it would look like between 2 pi and -2 pi. The domain of the sine function is all real numbers. And the range, well, the lowest this sine function will go is -1, and the highest it will go is 1. The cosine function works very similar to the sine function, except for the cosine function starts at 1, because the cosine of 0 is 1. And then the cosine at pi over 2 is 0. And then the cosine of pi is -1, and then the cosine of 3 pi over 2 is 0, and the cosine of 2 pi is 1. And then it'll follow the same pattern on the other side. And his domain and range are the same as sine, so the domain is all real numbers, and then the range is between -1 and 1. The tangent function looks like a bunch of cubics, but the tangent function is undefined at the pi over 2's because the tangent is sine over cosine, and cosine is undefined, or cosine is 0 at pi over 2, so the tangent function is undefined there. And so at any pi over 2, the tangent function is going to be undefined. And then there you go. This is just a brief sketch of the tangent function. His domain is x can't be any of the pi over 2's. That's the easiest way of saying it. And then his range is all real numbers. Secant, you guys can go ahead and graph that on Desmos. I also have it in our finish notes. 2 to the x is our exponential function. So again, you can use a table of values to graph it. 2 to the 0 is 0. 2 to the first is 1. 2 to the second is 4, so it would be up here. 2 to the -1 is 1/2. 2 to the -2 is 1/4. And so I always think of exponential as ramps. So it has a horizontal asymptote right here, so it will never equal 0. And so the domain of this is all real numbers, and the range is y is greater than or greater than 0, so it goes from 0 to infinity, but not equal to 0. The logarithmic function is the inverse of the exponential function, meaning I can flip-flop all the x's and y's. So I would have the point 0, 1, 1/2, -1, and then like this, and so it would look like this. So they are mirror images. The exponential graph and the logarithmic graph are mirror images over the line y equals x, and their domain and range are images of each other. So the domain, x's can go from 0, it won't equal 0, and then to infinity, and then your range is all real numbers. 1 over x is a rational function. They have asymptotes. We'll review how to graph rational functions soon, but for right now, x can equal 0 and y can equal 0 on this rational function. And then he just kind of looks like sideways parabolas in the first and third quadrant. His domain is x can equal 0, and his range is y can equal 0. The square root function, the square root of 0 is 0, the square root of 1 is 1, and then it would look like the square root of 4 would be 2. So he's just kind of like half of a sideways parabola. His domain can go from 0 to infinity, and his range can go from 0 to infinity. And then this guy, we have y equals the square root of a squared minus x squared. You guys might not know what this is, but let's do some manipulations. Let's square both sides. And we would have y squared equals a squared minus x squared, and then let's add x squared to both sides. So I have x squared plus y squared equals a squared. We talked about this earlier when we were talking about relations and functions. If you guys remember, that is the equation for a circle. Since it's the positive square root, it's just the top half of the circle. So we're going to go up a, over a, and over a. So it's going to go in between negative a and positive a, and then up to a. If it was the negative root, then it would be the lower half of the circle. And then the domain of this, well, if you can check, the x values are going between negative a and positive a, and then my y values for the range are going between 0 and a. I'm going to have you guys complete the chart below for homework, so we'll just hold on to that. So let's go back to our notes. So the domain of rational and radical functions. So rational functions are the ones that look like fractions. So if I had f of x equals 3 over x minus 5, if you guys remember that everything works in a fraction except for the denominator can't equal 0. So if it's asking for the domain, we just say whatever the denominator is and say that it can't equal 0 and solve that. So if I solve this, my domain can be anything, but x can't equal 5 because if x is equal to 5, the denominator would equal 0. So for rational functions, if it's asking you to find the domain, you would just take its denominator, say that it can't equal 0, and solve. For radical functions, so radical functions are your square root functions. And then if you guys remember, you can't take the square root of a negative number. You would get an imaginary number if you tried to do that. So whatever's underneath the square root needs to be positive. So for instance, if I had f of x equals the square root of x minus 3, we need x minus 3 to be greater than or equal to 0. You can take the square root of 0, that's okay. So if I solve this, I would add 3 to both sides, and as long as x is greater than or equal to 3, it would work. So that's how you would find the domain of rational and radical functions. I think today we'll probably work on the Aquaria problem or do a Socrative or Desmos activity. Your homework is from the book tonight, and I also want you to do the second page of the functions worksheet that we just completed. And that's it, gentlemen. If you have any questions,